Yeah, you are welcome again. So we want to continue our discussion on partial differential equations (PDEs). Having explained that PDEs is dependent upon the knowledge of partial derivatives, and I said in the last lecture that partial derivatives are derivatives of functions having more than one independent variables. For instance, if we have y as a function, which is defined as y into t comma x. So we have a function y which is dependent on two independent variables t and y. So for instance, to make it clearer, you can have y is equal to s squared t plus t squared. So this is an expression that is assigned to y. So y is our dependent variable and it is dependent upon x and t. So it can be written in such form like we have in this equation here now. So we have y is equal to y into t comma x, telling you that there's an expression connecting y and t and x. And for instance, we have y is equal to x squared plus x squared t plus t squared. This is an expression that satisfies this condition that we have here now. So this expression might be anything. I just formed this one offhand. So it might be complex than this, and it might be simpler than this. So just know that whenever you see something like this, so this y into comma bracket t stands for an expression like this. This is an algebraic expression having two independent variables x and t. So it can be this equation that I'm writing below can be written in short form as you see it up here. So let us now continue our discussion. I told you that you can find the derivative of y with respect to x and call it the y over the x, so which is equal to, in this case now you are taking your t as constant, then you differentiate your y with respect to x. You assume that x is a variable now and t is a constant. So in this case, the y dash will give us a 2xt. You differentiate this one. So because this one is a constant, you keep it like that. So plus 0. So because there's no x variable here, so this is a constant derivative of constant is equal to 2xt. So likewise, our dy dt, dy over dt is equal to x squared plus 2t, because you can see here now that y is equal to x squared t plus t squared. So in this case now we are differentiating y with respect to t. So our x is constant. We now have y is equal to x squared because derivative of t is 1. So plus derivative of t squared, that is 2t. So we now have x squared plus 2t as we have in this expression now. Dy dx is equal to x squared. Dy dt rather, I'm sorry, dy dt, we are talking about dy. We have differentiated dy dx. Dy dx gave us 2xt. Now we are differentiating dy dt. I'm very sorry. Dy dt is equal to derivative of y with respect to t. So y is equal to x squared t plus t. So in this case now, our s is treated as constant. We now have dy dt to be equal to x squared because this is a constant, plus, and derivative of t is 1, plus the derivative of t squared is 2t. So our dy dt will now be x squared plus 2t. And that is what we have here, x squared plus t. So that is dy dt. So from all these derivatives, we can do a lot of things. You can combine those things. For instance, you can form a partial differential equation. Like if I want to form a partial differential equation now, I can say my 2 dy dt plus dy dx is equal to something. So I formed a partial derivative. So this is a partial derivative. So partial derivative is a function or an expression. Partial differential. I formed a partial differential equation. Rather, I'm sorry. I have formed a partial differential equation now. So I form a partial differential equation from my dy dt and dy dx. This type of equation is known as known as a PDE, a partial differential equation. So partial differential